Good morning, Amherst. Welcome to the Monday morning edition of Chemistry at Home. Listen, this is going to be a long lesson, and we're going to start with a lot of notes. So you might want to pause this, get your notebook, get your reference tables, get your calculators. There's going to be a pretty good number of notes here, the longest lesson we've done so far. All right, welcome back. Colligative properties of solutions. Colligative is a silly word. It means of the collection. So when you have a solution, you've got your solute particles and your solvent particles in there. And the idea is the bigger the collection, the bigger the effect. The more particles you have dissolved, the bigger the effect on that solution. So there are four categories for colligative properties: vapor pressure reduction, boiling point elevation, freezing point depression, and osmotic pressure. The middle two are the important ones. That's where the math comes in. We're going to talk about these probably in reverse order. Least important first. So, osmotic pressure. You may remember doing the red onion cell lab in bio, and you had fresh water and salt water in a red onion cell, and the cell wall was semi-permeable, so the water can get through it, but the salt can't, so it lets some things through and not others. And if you had a saltwater environment, the water from inside the cell would rush through the cell wall to try to dilute the environment out there, and the cell would shrink as a result. And if you put it back into fresh water, water would come back in to the cell and it would get bigger as a result. Well, the desire for that water to achieve a more consistent concentration on both sides, that desire is osmotic pressure, the water wanting to rush in to dilute the salt water. Okay, the basis for reverse osmosis for desalination plants and whatnot. It's not something that you'll see tested. It's mentioned, but it's not that important in the greater scheme of things with regard to assessments. Freezing point depression basically means the freezing point is going down. So if you've got salt water, let me get a page to block this. You've got your molecule ion attractions going on here. You've got your positive ion, you've got your negative ion. You've got the negative side of the water being attracted to the positive ion. You've got the positive side of the water being attracted to the negative ion. And the molecule ion attraction interferes with the ability of the water to attract another water. When water freezes, it leaves the salt behind. So like the polar ice caps, that's fresh water. That's not salt water. If you were to take the snow from North Pole, that came from an ocean, it's fresh water, it's not salt water there. So when water freezes, the water gets together with the other water and it forms a crystal through hydrogen bonding. So you got your positive side of the water being attracted to the negative side of the water. It gets together in rings and it has a crystal structure, and there are a bunch of different ways that the crystals can form, and you can study that later. Understand though that the ions in between the water molecules are going to make it harder for the water to attract more water. So the water has to get colder, that solution has to get colder before the water can freeze out of it. So the liquid water must get colder than 0 degrees C before it will freeze. The higher the concentration, the higher the molality of the salt in the water, the colder the water must get before it can freeze. Makes sense. More particles, more effect. Freezing point gets 1.86 degrees colder for each molal of concentration. It's 1.86 degrees per molal. At this point, get your supplemental reference table. Table 1 lists 1.86 degrees right here. Molal freezing point depression. It's a physical constant for water, but it should say per molal. Right below it, the molal boiling point elevation, 0.52 degrees C, should say per molal. So please add that right now. See if I can zoom in on that. Okay, add those per molals. Why is that? Well, boiling point elevation is a byproduct of vapor pressure reduction. We know that vapor pressure is a function of temperature, and temperature only. So here's vapor pressure, here's temperature, this is like table H, And if you get up to 1 atmosphere normal pressure, that temperature is the normal boiling point, which for water is 100 degrees C. Well, in order for a molecule to evaporate, it's 3 things have to happen. We know about this. It's got to have sufficient kinetic energy to overcome the intermolecular forces. Okay, that's E sub A on the charts we talked about in our last unit. It's got to be at the surface. That's a big deal. And of course, it's got to have proper orientation, be moving in a direction away from the other molecules. Well, when you have a solution going, you've got solute particles taking up some of the valuable surface area. Now, you'll see this terminology. They call this a non-volatile solute. That means it doesn't evaporate. It has no vapor pressure. Sugar and salt, they don't evaporate. They are non-volatile solutes. But if you have sugar or salt, any non-volatile solute is taking up some of the valuable real estate at the surface, so fewer water molecules are able to evaporate and your vapor pressure goes down. If vapor pressure goes down, look what happens to your chart. Here's pure water with normal vapor pressure, and we said there's 1 atmosphere, and here's 100 degrees Celsius, the normal boiling point. The purplish line here, red, looks like on the video, if this is a solution at a lower vapor pressure across the board, look what happens to the boiling point. It goes up. It's higher than 100 degrees C. So the higher the concentration of non-volatile solute, the lower the vapor pressure, and consequently, the higher the boiling point. It goes up 0.52 degrees per molal of solution. So that's the 0.52 here. It's not the only thing to consider, though. It'd be simple if it was, but it's not. You've got the Hoff Factor. That's the scientist's name. Non-electrolytes, things like sugar, things that don't dissociate when they dissolve in water, have a Hoff Factor of 1. What does that mean? If you take glucose, C6H12O6, if you dissolve it into water, it stays C6H12O6. It's just aqueous now. This is not a dissociation equation. This is just a dissolving process. It's a physical process. But for every 1 particle of sugar you put in, there's 1 particle out, so to speak, in solution. So a 1 molal solution of glucose, aqueous, has a freezing point that's 1.86 degrees below 0 and a boiling point that's 0.52 degrees above 100, or 100.52. And if it's 2 molal, it's going to be twice as far. So 2 times 1.86, negative 3.72 for its freezing point, and 2 times 0.52, which is 101.4 for the boiling point. So you add it on to 100 or subtract it from 0. So what you're doing is you're extending the liquid range. So here's pure water. Below here to the left it would be solid, above here it would be gas, but it's liquid between 0 and 100 degrees Celsius. Well, if I dissolve sugar into that water, if I make a concentration at 1 molal, the boiling point goes up to 100.52, the freezing point goes down to negative 1.86. If I make it twice as concentrated, excuse me, take it up to 2 molal, I'll go up twice as high, 2 times 0.52, all the way up to 101.4, and twice as low, 2 times 1.86, negative 3.72. I'm extending the liquid range. So the higher the concentration of solution, the greater the range of the liquid. Here it is liquid water, but if I have solution, the boiling point goes up, the freezing point goes down. Electrolytes, on the other hand, you get more bang for your buck. Acids, bases, and salts are called electrolytes. They'll have dissociated ions in solution. Dissociated ions create more particles. More particles creates more effect. So in a Hoff factor, for an electrolyte, it's always greater than 1. What am I talking about? Okay, so here's sodium chloride, solid, dissolving into water, creates Na positive ions and Cl minus ions. You could find a lot of dissociation equations, not a lot, but a handful of them, at the bottom of table I. Right here, all these ones with H2O over the top, those are dissociation equations. So here's NaCl turning into Na positive and Cl minus. It's just an example. But for every one particle of salt that dissolves, I get two particles that are in solution. One particle goes in, two particles come out. So I'll have twice the effect. The Van Hoff factor is 2. They say I for the Van Hoff factor. What if it's calcium chloride? One particle goes in, I get a calcium plus 2 ion and 2 Cl minus ions. 1 plus 2, that's 3. The Van Hoff factor is 3. It's going to have 3 times the effect. So a 1 molal solution of salt will have the same effect as a 2 molal solution of glucose because it creates twice as many particles in solution. The change in the freezing point depends on your molality. It's 1.86 degrees per molal and your Van Hoff factor. The change in the freezing point. Take your molality, multiply it by 1.86, multiply it by your Van Hoff factor. Boiling point, same deal. The change in the boiling point, take your molality, multiply it by 0.52, multiply it by your Van Hoff factor. These numbers, the 1.86 and the 0.52, they don't change. They're constants. Okay, so now we're getting into the math. It's important to remember these are the change. I see people sometimes they want to plug in the problems. They'll try to plug in like 100 point something. No. The change is the point something, not the 100. I'll show you what I mean. So here's an example. If you've got 20 grams of sodium hydroxide solid dissolved in 250 grams of water, what are the freezing point and the boiling point of the solution? Well, NaOH had a GFM of 40, 20 grams, that's half a mole. 250 grams of water, that's 0.25 kilograms. Molality is moles over kilograms. That's a 2.00 molal solution. NaOH is an electrolyte. It's a base. It's going to ionize. So it's going to dissociate into mobile ions in solution. Its Van Hoff factor is 2. So 2 molal times 1.86 degrees C per molal times 2. It's going to change the freezing point 7.44 degrees. So your actual freezing point is going to be 0, which is a definition of the original freezing point of water. It's not for sig figs. Minus 7.44. Your freezing point is negative 7.44 degrees. So you take your number and subtract it from 0. For boiling point, the change in the boiling point is 2 molal times 0.52 times 2. You're changing your boiling point, well, for 2 sig figs, it's going to be about 2.1 degrees Celsius. So add that on to 100. The 100 doesn't affect your sig figs. Your boiling point is going to be 102.1 degrees C. All right. Second example. I know I'm moving fast, but you can rewind this video. Example number 2. A solution of calcium chloride, it's got a GFM of 111.1, aqueous, has a boiling point of 105.3 degrees Celsius. If the solution contains, pardon my grammar here, 500 grams of water, well that's half a kilogram of water, how many grams of calcium chloride are in it? Okay, you've got a solution, it's got this boiling point, it's got this much water, how much salt is in it? Your change in your boiling point is 5.3. This is where people go wrong. They want to plug in 105.3 into the equation. That doesn't work. Calcium chloride will have a Van Hoff factor of 3. So the change in the boiling point is your molality times 0.52 times your Van Hoff factor. So 5.3 is your molality times 0.52 times 3. Divide out. You've got a molality of about 3.4. Just leave that string in your calculator, just like we did in the earlier problems. So you've backtracked it, you've solved it for molality, and understand that molality is moles of solute over kilograms of water. You had half a kilogram of water, so your 3.4 is your number of moles divided by 0.5 kilograms. You can do it algebraically or dimensionally. I did it algebraically here. Cross multiply, solve it for x, and you've got about 1.7 moles of calcium chloride. Leave that string in your calculator, use your GFM, down to 2 sig figs, that's about 190 grams of calcium chloride that would have been dissolved in that 500 grams of water. All right, so these problems, it's a little bit of algebra, a lot more notes than we're used to doing on video, but that's okay. So worksheet 7, colligative properties, is broken up. You've got non-electrolytes, 1, 2, 3, 4, 5 problems there. When they say non-electrolytes, these are things that don't create mobile ions. They dissolve, but they remain molecular. Okay? First page, 5 problems. Van Hoff factor is 1. Next page, electrolytes, the Van Hoff factor is always greater than 1. This is where people tend to go wrong. We did NaCl, we did CaCl2. Consider what's your Van Hoff factor for something like ammonium sulfate here, if you look at number 8. All right, ammonium sulfate. What's your Van Hoff factor there? Calcium carbonate. This is a ridiculous question, by the way, number 9. What's the change in freezing point? 175 grams of calcium carbonate are dissolved in 45 mils of water. Well, limestone doesn't really dissolve in water very much. Carbonates are not very soluble. I doubt I'd get 175 grams into 45 grams of water, but bear with me. The ridiculousness of the problems don't negate the math. All right, so you've got a handful where you've got up to number 10, so 6 through 10, Van Hoff factor greater than 1, and then a couple mixed problems. All right, and then percent by mass 1. 14 problems. This is rather extensive homework, but we've all got a lot of time on our hands. All right, I'm going to post it up. Email me questions along the way. Keep moving forward, and we'll take it from there. Take care.